I think this comes from a Chicago math competition. We're supposed to find the product of the composition of this quadratic polynomial with itself, okay? Now, again, the product of the zeros of the polynomial would just be 2, trivially, but we're supposed to find the product of the real zeros of the function composed with itself. Now, this very first statement, we'll just let R be a 0 of P of X, since we're trying to find the product of the real zeros of P of X. But notice this means right here, this means the very same thing as the polynomial evaluated at the polynomial evaluated as 0. I mean, at R, excuse me. Now, y'all, root and 0 is a synonymous thing. Okay, so that's what that means. Okay. Now, what does that mean, though? It follows that P at R is a 0. P at R itself is a 0 of P of X, is what this all implies, okay? So let's carry on. Now, it makes sense to find the zeros of the individual polynomial because we're going to have an equality condition here. So I went through this fairly quickly. These are the zeros of the polynomial itself, of P of X, okay? But since P of R is a 0, we have to equate P of R with these zeros, right? This requires a little bit of notational fluency, I guess, Okay, so from that point on, it's fairly straightforward. There's 2 zeros right here, so you have 2 different equations to analyze. Now, if you'll take a look right here, both of these statements, to find the nature of the solutions, is just the discriminant. So in other words, this would be b squared, where b is the usual coefficient of the linear term in a quadratic. And the rest of this is minus 4ac. Okay? And again, that's all the way down here, folks. Here and here, this represents the discriminant. Now, down here, you can see the discriminant is negative. And that's because 2 times root 17 minus 2 root 17 is a number less than negative 8. See, the square root of 16 is 4. 2 times 4 is 8. So this has to be less than negative 8, right? Just this term right here. Okay, this part right here has to be less than negative 8. That means this entire discriminant has to be less than 0. So there's only complex solutions here. Complex. Okay, I'll just write that. Complex solutions. I haven't learned how to write very fast here. So these are complex solutions here. We're not interested in that. We're trying to find the real solutions. And these are these are going to be positive solutions, right? And so that means that we're only interested in this top part, okay? Now, so the answer is going to be just this circled part, because the constant term is the product of the zeros or the roots, okay? So that's the answer we're looking for, folks, because literally this is the product of the zeros of the function composed with itself, all right? Because these conditions have to prevail. So this is our solution because we have the positive discriminant here. Now, if you're not seeing that, just think of it like this. If you have R minus A, where A is a 0 or a root, times R minus B, where 0 is a root or a 0. Okay, let me write this like this. Equal to 0. Okay, of course, this means the same thing. This is just Vietas for the quadratic. This is equal to, this is equivalent to R squared minus A plus B. And then again, plus, these minus signs cancel when you multiply, so you have plus AB. So you see, A and B are explicitly zeros, right? That means the constant term is the product of the zeros, which is exactly what this is. So this entire part is our answer right here. This part that I've circled is the answer. Kind of a neat problem. It'd be fun to see how this would work out if you composed it 3 times. I don't know if it'd be maybe a little bit more uglier. I don't know if there's a nice way to generalize it. But anyway, that is the solution, folks. We ruled these out because of a negative discriminant. This is what's left, and that's the answer to the problem. Thank you for viewing.